So with this slide set, we're really zooming in on, once if you imagine, a rainy day and rain hitting the soil, then what happens? Or when you go to water your pot, or if a farmer is setting up irrigation in his field. So I'm ignoring the plant for right now. And then the next slide set that's posted on water movement in the plant will be like a whole separate topic. And so when we look at water in the soil, I think we worked through some of this information on this slide set. So I edited the side of letter there. So very often in plant physiology realm, we don't just put psi, we put psi sub W. Okay, so psi sub W is more official for what is the overall water potential. Okay, and then we looked at, I think we went through this slide last time where we're looking at the use of water potential. It's just a useful way to describe how water is going to move in a system or between two systems. And so there's this equation, very much, there's like this water potential equation that can get used, and depending on what you're thinking about, it can be kind of a long equation or a shorter equation. So it's kind of interesting how it shifts depending on, are you talking about the soil, are you talking about what's going on in the plant? And so basically, but overall, what you can say is that water potential flows from a higher water potential to a lower water potential. And I think the analogy of a waterfall can be useful. The author of the book uses that too, and I think that's relevant. So, if you look at a waterfall, you would say that at the top of the waterfall, you have high water potential. At the bottom of the waterfall, there's lower water potential. And, we know that water doesn't, at least on this earth, water does not flow up the waterfall. And so we measure water potential in units of pressure. Typically it's megapascals or pascals, but you could use atmosphere. And I think we might have left off around here just defining what atmosphere is relative to megapascal. You don't need to memorize that. It's just if you're curious, that's the conversion. All right, so water potential, when you think about water moving through, not quite sure why it's doing that. Okay. When you look at how water is moving through the soil, you can think about gravitational forces. That will be part of it. So they actually say there's a component to the water potential equation that's called psi sub G. And then there's a so-called matrix potential, which they abbreviate as psi sub M. And matrix potential is describing essentially how you have water having adhesion, which means they like to cling on to soil particles in this case. Water also likes to do cohesion, which is water to water bonding. Right, so you have both of those being taken into consideration for the matrix potential. And then also there's this so-called osmotic potential, psi sub F. Osmotic potential. So I like to think of the F as the solutes that are dissolved in the water. So soil water is not pure water. There's going to be stuff dissolved into it. And so it can be minerals, it can be fine organic matter, chemicals, for example. But you often need to think about inorganic fertilizers. Remember, when you fertilize your crops, essentially those inorganic fertilizers that are being used are minerals. They're salt minerals. And so those are solutes as well. And so often you might hear someone say, oh, we're thinking about the dissolved salt, but that's in general, solute is the other term to just kind of in general say whatever's dissolved in the water. Then we start saying the word solute. So then really when you start looking at the overall water potential, you can piece these all together. And so you have the overall water potential, and you can say it's equal to psi sub g. Whoops, that's supposed to be a g. It won't work. Plus psi sub m plus psi sub s. Okay, so you can just keep tacking on. And then, yeah, I'll introduce, there's another one coming into play here that you'll see, which is psi sub p. We'll talk about that one too. All right, so the overall water potential equation, depending on what you're looking at, you can have, like in this case, you have a lot of factors to think about. And sometimes we can just zoom in on certain aspects of it because some of them become irrelevant in different systems or not as relevant. So this is from your textbook, these images showing that, when you water or irrigate or a rain event, adding water into soil, here they're looking at an irrigation canal in the far lower left. And what they're showing or trying to show here is that when you have this irrigation canal, certainly gravity is going to influence how water moves. You're going to have water moving straight down, right? But then in order to get water to move out into the soil more laterally, you have to think about matrix potential, that psi sub m component, which is looking at how water adheres to soil particles, how water adheres to itself. And so you tend to get this, they often refer to the movement of water in the soil or in the plant. They'll use the word bulk flow. Bulk flow, F-L-O-W, we're looking at the idea that water molecules, because they like to bond with each other, to have that cohesion, they tend to move as a solid mass of water. So you don't have a bunch of breakup of water molecules independent from each other. You have like this stream of water going out into the soil. And so it moves by bulk flow en masse. They also to that word too. They'll say it moves en masse through the soil. Gravity certainly plays a role in this. You have, pulling down on the water through the soil, but then the matrix potential allows for water to move more laterally, which is good. You want your irrigation to spread out. You want that water to spread out. And so you need to have soil wet enough, though, in order for lateral movement to occur. And so it really does kind of mess with things if you don't water frequently enough to the point where your soil gets really dry. You can end up in a situation where even though you water, it'll just kind of go straight down through gravity and it won't move out laterally because the soil particles are so dry, you cannot get that capillarity flow of water out in a more lateral way. And so they often will tell you, if you have that real dry condition, especially in potted soil with, they notice this especially with some of the potting soil mixes that you can buy that have a lot of peat moss in there too. You'd think that would be good, but it can actually create a situation depending on how the peat moss is distributed in the pot where you just get local water and it won't flow out. And so dry pots are difficult. You have to be careful. So they actually will say if that happens, you should really just get the whole pot of soil wetted and then go back into drip tube irrigation after that. And so they're saying that you got to be careful if you let your soil system, whether it's in a irrigation field, a big plot of land, or in your pots, if you let them dry out too much, you might not get that capillary flow or bulk flow of water moving out from the point of application. And so that it's just a practical thing to think about when you're working with plants. And I always have to keep it in mind because I tend to forget to water like my office plants or my house plants, and then I'm confronted with these issues. So, okay, so there are some real practical things to think about when you are working with, okay, how does the water move through the soil? Let's look at this idea too. And so the SISA-BS component, that's the solutes that are dissolved in the water in the soil. And that can really play a role, especially in more artificial soil systems like an agricultural field, where you've been applying lots of fertilizer and maybe you don't know what you're doing, and so maybe you overdid it. And so now you have lots of fertilizer or inorganic matter, chemicals. So they just tend to call those salts. So the inorganic fertilizer salts build up in the soil. And what that does, when you look at your SISA-BS, anytime you dissolve anything into water, pure water, what that does is it lowers your SISA-BS value. Now, SISA-BS, anytime you put anything, dissolve anything into water in this case, it drives your SISA-BS to be a negative number. So it's a little weird because you have to think about the negative scale now. And so the more you dissolve some solutes in, the more negative that SISA-BS value becomes. All right, more solutes, more negative SISA-BS. More solutes, more negative SISA-BS. So that SISA-BS component basically can create situations where if you have a high salt in your soil, it can actually create a situation where the plant has a really hard time taking up water from the soil because soil water is so salty. And so what we're starting to think about here now is the idea of osmosis. And so if you think back to that definition, what I'm talking about for osmosis right now is the movement of water across the selectively permeable membrane, which is the root tissue and the root cell. Okay, so if you have those plants where their roots are in a really salty, the soil water is so salty, you can actually create a situation where water comes out of the plant rather than in. That's the exact opposite of what you want. And so this is why you have to be so careful about your fertilization schedule and amount. You really got to know what you're doing, because obviously if you're trying to grow plants, you don't want water coming out of them. That's going to kill them eventually. And so here in this image, they're showing two different plants put into beakers. The one on the left is a beaker of water with salt dissolved in it. The one on the right is pure water. And what they're trying to show here is the left one's looking really sad because it was unable, even though its roots are soaking in water, but it's salty water. And it's salty enough that the plant is losing water out of its body into that beaker of salty water. So it's actually dehydrating the plant, even though its roots are, it's in a liquid medium, it's in that water, but it's just too salty. So that SISA-BS value, anytime you have salts dissolved in the water in this case, it's going to make your SISA-BS very negative. And we said that water moves from a high water potential to a lower water potential. So another way to say that is that water moves from less negative to more negative. All right, so in this case, if your SISA-BS is really negative, that's going to drive your overall water potential. Where did it go? So if you have your psi sub S component very negative, it's going to drive your overall water potential to be negative. And another way to describe the movement of water, let me go back to the slide where it says, so it's from high to low. Another way to say that, depending on the situation, is that it's going to move, water will move from a less negative water potential, that's supposed to be an arrow, to a more negative water potential. So if that psi sub S is creating a really negative situation, then you would start saying, well, water moves from a less negative water potential to a more negative water potential. And so looking at what's dissolved in the water can have a big, big impact on overall water potential, and then how water is going to move in that system or between two different systems, like the soil water and the plant. So what we're talking about here in this case with the saltiness actually sucking water out of the plant is this idea of osmosis, where it's often described in something like this, where they show a YouTube. Anytime I say YouTube, I don't think about this kind of YouTube. But anyways, you have a YouTube, and then right in the middle, there's a permeable, semi-permeable membrane. And then here they're showing, let's fill it with water, equal amounts of water on either side. And then they said, okay, let's add some sugar. So that's your solute. So that's impacting your psi sub S. So as you add more solute, you are altering your psi sub S component. You're driving it more negative. So what's happening here is that this part of the system on the left of the membrane, because you've added that solute, you've made your psi sub S value more negative. And we just said that water moves from less negative to more negative. If you have pure water on the other side of that U-tube, that overall water potential, because there's no psi sub S component messing with it, that overall water potential is less negative. All right. So then they're trying to show that water is moving from the right of the tube through that membrane into the left. Okay. I don't know why it just disappears sometimes. Okay, that's supposed to be an arrow. Moving. So water is going to move through that membrane and go into the left side where the sugar is dissolved. You could say, one way to phrase it is that the water wants to dilute out the sugar to make it an even concentration. So you can think of it that way if you want. But really what's really happening here is that the minute you dissolve anything into water, you get a psi sub S component and it's negative, because it introduces chaos into the system and it lowers the free energy. So then pure water doesn't have a psi sub S. There is no, it's zero. So you don't have any negativity on that side. In this case, with pure water, it's zero. So less negative to one. The bottom U-tube is trying to show two different concentrations of glucose dissolved on either side of that membrane. And again, water is going to move to where there's more solutes dissolved, because that side of this side here, its psi sub S is more negative than the left side, because there's more solutes. More solutes, more negative psi sub S. So as long as you keep that in mind, anytime you dissolve anything into water, you have a psi sub S and it's negative. It's going to be some negative value. And then that will impact your overall water potential. It'll start driving your overall water potential to be more negative. And then that will help you figure out how water is going to move. Will water move into my plant as I'm irrigating this field, or do I have way too many fertilizer salts in the field and it's actually creating a situation where water is going to get sucked out of the plant? And so that's, you might have heard the term fertilizer burn. That's what they're referring to. They're referring to the idea that you're actually getting the reverse of what you want. You're getting water exiting out of the plant because the water in the soil is too salty. Your spice of S is so negative that water's following the less negative to more negative idea. And so it's coming out of the plant into the more negative water potential in the food. So obviously not something you want. And so again, if you're going to fertilize, they often like, you might read a website where they say, if you haven't changed or refreshed your potted soil, soak your soil, that pot, into some water to really kind of flush out some of the salts in the soil. Or they'll just say, or put repot it with fresh potting soil, because especially in pots in your house plants, you're going to get a buildup of salts if you fertilize on a regular basis. Yes, the plant takes up some of those, but not all. And so in a very small pot like that, you got to be very aware that you could be causing burn, fertilizer burn, if you over fertilize and don't flush out the minerals now and then. Okay, so I'm kind of stingy with my fertilization schedule on my potted plants because I worry about this. My one grad student, Scott, he's graduated now and is teaching in a university in Minnesota, but I have potted plants in my office, and he came in to chat about something, and he noticed the surface of my soil was all like this gray, crumbly looking stuff on the surface. And we were, looking at it. I said, yeah, I just noticed that the other day. I finally paid attention and saw that. I said, I don't know if that's a fungus or what. He licks his finger, puts his finger on it, then licks his finger again. He's like, oh no, that's salt. And I'm like, what are you doing? The safety modules you have to take for every science lab. It's like, do not do that. So apparently he was not thinking too much. But he's like, oh yeah, that's just salt. So that tends to happen with potted plants. You'll get the salt kind of rising up through, because the water is evaporating out of the soil through capillary action, and the salt come with it, and then they get deposited on the surface of the soil. So if you start to see the surface of your soil looking, in my case, it was like a whitish gray color, chances are it's a buildup of salts, and it's like, start taking care of your plants, repot them, give them some TOP. Okay, so this can be a real practical thing to think about, whether you just, have houseplants or if you are trying to grow crops for commercial purposes. So there's some other terms that I'd like you to think about. And you have the saturation idea, which is basically, if you think about a nice drenching rain, what happens is that the soil pore spaces get filled with water, and there's really no air in those pore spaces. It's all saturated with water. And then we would say that the overall water potential is pretty close to zero in those conditions. Not exactly zero, but pretty close to it. If you, then if you think, okay, the rain went away, you have gravity acting on that water continually. Gravity doesn't stop. So you're going to have water trickling through the soil, down, 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 eventually into the water table. And if you think about the different sizes of pore spaces in the soil, there's, the bigger pore spaces, the macropores, the micropores. So first you're going to get water will leave more easily out of the large pores, and then it's harder to get it. So it takes longer for the water to exit out of the small pores, because the water likes to cling to the soil. And so you keep having this happening until you have the cohesion and adhesion forces equaling out to the gravity force, and then the water stays put. And then that's what they call field capacity. Okay, field capacity. So basically, it's after the water has stopped draining, then you're at field capacity. And so you hear agronomy and agriculturists, they talk a lot about field capacity, and different soil systems will have different field capacity. It depends on the pore spaces. It's really highly dependent on your soil texture and composition. And so when you look at the soil water really start thinking about the pore spaces. How big are they? How small are they? And then here you're looking at a gradual loss of water from left to right in this soil. And so the figure A is most, pretty much field saturation. And then you start seeing the, gravity is going to bring the water lower down. And so they're trying to show in figure B that the bigger pore areas, that's where the water exits first. All that white is air now. And then the figure C, you're looking at soil particles that there's, a lot of water has left that section. And one thing to pick up on here is how when water starts to, you have these cohesion and adhesion forces. Do you see how water is curving at the air-water interface? You have these curves that are going on. All right. And that in the figure B, you don't really have any kind of significant curving at the air-water interface, not like what you do in figure C. So I want you to kind of get that in your head, think about it for a second, and I'm going to come back to this. But that curving like that causes an interesting force that starts to get generated. And so, if you start thinking about this movement of water by gravity pulling the water down, you can get this gradual shift where the macropores lose water first and the micropores, and then you can end up in a situation where you have water clinging to the surface of the soil particles and kind of forming this film around the soil particles, and you get these curves going of the air-water interface. So that field capacity idea was, if you think about the water that's still in the soil after the excess water has drained away. And so you can put a number on that. You can actually calculate that. And then you have your permanent wilting point, which is a sad, sad thing. This is when the soil has a water content that the overall water potential is causing the situation where the roots start to get water sucked out of them. So then your plant starts to wilt. And even if you put them back into water, like you do everything you can to rewater that soil, but they just stay permanently wilted. And I've done this to a few of my house plants where I've gone on vacation, forgot to set up automatic watering, come back, and they're permanently wilted. No matter what I do, they won't take up water again. They're done. And so even if you put them in 100% relative humidity, they're done. And so obviously you don't want that to happen. You can put a number on this, but it varies for different plants. So this phrase here, it says when soil reaches an overall water potential that is less than what they mean in this case, it would be more negative. Less than would be more negative. An overall water potential that's more negative water potential. Wilting point, not a good thing. So we need to think about available water. So this is kind of like that beaker, those two beakers where it was salty water. There's lots of water in that beaker, but it wasn't available to the plant because there was too much salt dissolved in that beaker of water. So available water is the amount of water that the soil can hold that's actually available to the plant. The plant will have the ability to bring it in. And they actually do a calculation for that. It is the difference between field capacity and the permanent wilting point. And water is actually more available if you have moisture that's closer to the field capacity number than the permanent wilting point number, which makes sense. And then the other thing to consider in a field, especially, is that you can have gravity, certainly pretty good effort of gravity, pulling the water deeper and deeper and deeper into the soil. And so if water is draining away from the top, there's still water in that soil, which is further down. And so again, when they say not uniformly available, that's also referencing different plants will experience different available water because of root systems. So if they're a shallow rooted plant, after gravity drains the surface water, they're kind of out of luck. But the plants that have the deeper root systems, they can still have available water that they can pull up. So it really does depend on the plant and what its root system is. This is just trying to give you the idea that root systems vary tremendously in terms of overall design, but also if they're shallow or deep. And in some regard, you can influence this by how you water your plants. So if you water deeply, for example, if you have a lawn that you're very happy with and you want to keep it alive while you go on a 3-week vacation to the Caribbean, the goal would be leading up to your vacation, you would water your lawn deeply and for a long stretch of time. But then in between those waterings, give a good length of time in between. So what you're doing is you're forcing or you're encouraging your roots of the grass to grow deeper when you do that. But if you just water a little bit at like 10 minutes every other day, what's going on there is the root systems stay more towards the surface. That kind of watering schedule promotes more surface shallow growth of roots. But if you do a deep water and then let it be for a week or two, that causes the roots to kind of seek the water. They'll kind of follow the water down. And so you get the longer roots. So to some extent, you can influence that idea. So now let's think a little bit about what happens when you take the plants and they want to start taking that water from the soil up into their body. When they do that, it's actually the root hairs that do the majority of that. Their root hairs are really well designed for water and uptake. So they're trying to show here that water is in the blue, the air pockets are in the white. So what they're trying to show here in this picture is that the bigger pore spaces, you can have water, leaving and getting pulled up by the roots easier in the bigger pore spaces. But when you have water clinging to the smaller pore spaces, that water is harder for the plant to bring up because of some of the cohesion adhesion forces in those areas. So when they started looking at this issue and wondering, how does the root take up the water in the soil, they actually see that it's a tension force that allows for this to happen. And so it's kind of weird to think about liquid water having a tension put on it, but it happens. And so here you're looking at a syringe. So sometimes this analogy helps. If you put water into the barrel of the syringe like that, and then you pull back on the plunger, that's a tension force. You're creating a tension force by sucking on that water with that plunger like that backward action. And so if you look up the definition of tension, it's actually negative pressure. That's what tension is. It's negative pressure. So what we're doing here is thinking about the water potential equation, and in particular, the psi sub p portion of the equation, which is your pressure. pressure with regard to water. So they often refer to it as, whoops, hydrostatic pressure. Oh, I have it right next. Sorry. I didn't know that. I didn't look further. Hydrostatic pressure. So psi sub P can be part of that equation. And so we're talking about hydrostatic pressure. In this case, it's negative pressure, which is tension. And then you can't ignore the psi sub s, especially if you're in a field that has a lot of salts in it. Psi sub s will come into play. But if you're thinking about a more typical soil, like just out here, in a forest, your psi sub s values, because those are a more typical soil that isn't fertilized, isn't being managed in any way, your psi sub s component isn't super big or super negative. So you tend not to have much influence. And so it's really the psi sub P that's driving how water is moving once you think about how roots are involved in taking up the water from the soil. So a typical soil that's not being managed for ag purposes, the psi sub s is pretty negligible. So negative 0.02, which is, so most plant physiologists will just kind of say, yeah, let's call it 0 and let's ignore psi sub s, which I love that. So they just say, let's wipe psi sub s out when we start thinking about how plants are taking up the water. It's really a function of your psi sub P. All right, so as the roots are taking up water, what's happening is that action is creating a tension on the water molecules in the soil. And so if you can imagine the roots taking up water, and as they're doing that, going back to figure A again, let's say that, like you just irrigated your soil or your pot of soil. And then, so the macropores, those areas will get, that water's easily taken up by the roots. It's pretty easy for them to get access to that. And then you can imagine the macropore water is starting to get more, it's pretty much all gone. So then you start getting into the situation in figure C, where now you have that thin film of water on the soil particles. And that actually creates a pretty good surface tension. So remember, we were talking about water initially earlier and talking about how in a pond of water, you have the water molecules at the surface of that pond are actually more attracted to the water below them, the water molecules below them, than they are to the air molecules above. And it kind of creates this pulling action where the surface water molecules are kind of being held by the water below it. And so that generates a surface tension. And I'll try to convince you of that. And so the soil is drying out because, the plant's taking up the soil water. And so it starts to dry out. Macropores get the water, you can get that really easily. And then the micropores, you start pulling water from that. And then you imagine the soil particles, you got this water film clinging to the soil. And you can imagine the liquid water receding into tighter spaces and tighter cracks and crevices of the soil particles, kind of like in figure C there. And so then you get those curves that I had pointed out in an earlier slide, where you have these curves at the air-water interface. And the fancy word for that is menisci or menisci, or the meniscus disc. You might have heard that. I mean, if you've had to measure something out in a graduated cylinder, they say, look at the meniscus disc at the air-water or the whatever liquid, the liquid-air interface, and measure that. And so what is happening is that curvature, those menisci is actually causing a tension. All right, and I'll try to prove it to you in the next slide. So that surface tension or tension, there's an equation which I'm not going to ask you to mess with, but it's important for you to think about it. It's this one: phi sub P is equal to negative 2T divided by R. T is just a constant. It's the surface tension of water, which is 7.28 times 10 -8 megapascal. And then the R is the curvature of that meniscus disc. How big is it? How small is it? And that's a graduated cylinder showing meniscus disc figure there. So remember now, anytime you put a small number in the denominator of the equation, it makes the overall number very big. In this case, it'd be a very big negative number. So if you have a really small radius, so in the figure C here, where you have smaller and smaller radius there in between those little tiny soil particles and those little tiny cracks and crevices, that's going to drive your overall size of P to be a really big negative number. That means it's really good, strong tension. You know, a nice big size of P, a nice big negative size of P is a nice big negative pressure or a really good tension. And so what you see happening is that right at the roots, where the roots are in the soil, you get this strong tension originating right where the roots are, in that soil water right there. So right by the root zone, the water right there has a pretty good tension on it, real strong tension. But further away from the roots, just in the bulk soil out there, there's not as much tension. And so what you have then is a tension gradient. If you can see a gradient of some kind like that, where it's really high tension by the roots, lower tension further out, that's your gradient. You're going to get water moving toward the roots in this case. It's like the roots are sucking the water. If you want to think of it that way, it's like the hypodermic plunger idea that I showed you. It's like the roots are sucking on the water and taking up the water through that kind of suction action, sucking action. So it's a gradient. And as long as the water molecules are cohering to each other, where it's like a solid mass of liquid water, they're all connected. There's no like huge gaps of air in the pathway. As long as it's all connected like that, you'll get water movement. So really, when you start thinking about roots, plants in the soil, then you really start to zoom in on the size of P value of the water potential equation. If it's an ag soil, you do have to think a little bit about size of S for sure. Yeah, but in general, if you just think about in general, how is water moving towards the root, you really zoom in on the size of P that has the biggest impact in a typical non-ag soil. Okay, so this tension gradient idea is what we're thinking about. Have I convinced you? So it's, I don't know, when I think about what's happening in the soil, I first I ignore the plant, just think about what forces act on water, just in soil in general. And that's what I was trying to do with the initial slides. And then it's like, okay, now let's add the plant in. Now what seems to be playing the biggest role? And in most cases, it's the size of the P, that tension. That's what's really driving water movement into the plant. But in egg soils, you got to also remember about the size of S. That can cause problems. Can actually reverse the water flow out of the plant if the size of S gets too prominent. So what we're thinking about now is that the water has been brought into the roots. And that's not, of course, the end of the story, because now the water has to get used by the plant, and it actually will get brought through the whole plant body. And so in this picture, they're showing how it's getting into the xylem. That's the primary job of the xylem, is to move water through the plant body. And ultimately, it's that water is going to get to the leaves. And then we're going to see that once it gets to the leaves, it'll get shifted into water vapor, and then it'll exit out of the leaf as water vapor into the atmosphere. And so that whole method, that whole process. So we're going to kind of think about, what's causing that to happen. Like bringing it into the roots is one thing, but how does the plant get that water all the way up to leaf, which is pretty considerable when you start thinking about like giant redwoods or giant sequoias. I mean, that's like, how in the world is it getting it all the way up? And so there were a lot of different theories and hypotheses being put out. And there is a leading one that seems to be describing the data that they're collecting. And it's actually pretty similar to what's happening in the soil with how the roots are, taking up the water. There's some similar mechanisms or forces at play with that. But before we shift into that, there are questions on anything. I know I just threw a lot at you, and water potential. The first time I learned water potential and all of that, it took some thinking. Where's the, no, trying to find the right, it doesn't show up on my slide. There it is. Yes, it's drained away, and yeah, it's so whatever water is left, and it's not continuing to drain away. So then they say that field capacity, and that's highly dependent on the composition of the soil particles. And a lot of it has to do with how many macropores are there, micropores are there. That has a huge impact. How many people are currently taking soil right now? Okay, handful. I'm sure you've been learning. Do they get into water potential? Okay, a little bit. All right, so Friday we're going to think about how does water move in the plant. Once it's in the plant and in the xylem, what's happening? And we're going to see some similar ideas here where we have to zoom in on SISA P for that as well. All right, we'll stop there.